In many ways, VR is a lie designed to trick our senses.
In this work, we help make VR a more effective lying system.
As children, we quickly learn that objects in the world around us persist even when we can't see them. This understanding is called object permanence by developmental psychologists. The children's game of peekaboo is an example of an object permanence test. To an infant without an understanding of object permanence, it appears as if the peekaboo player magically appears and disappears from reality. Virtual objects can contradict principles like object permanence. They can blink into and out of existence for no apparent reason. This is because VR has no objective truth, only perceived truth. It conforms to our expectations of reality not because it has to, but because it is constructed to. In fact, VR systems are constructed to create better experiences by invisibly contradicting our expectations. For example, redirected walking makes players feel as if they are exploring a large space as the physical system redirects them in circles. Recent work by Sun et al. Achieved this effect by quickly shifting the player's virtual orientation as their eyes naturally move between focus points. This process is invisible, meaning it doesn't break the illusion of objectivity. Redirected walking uses invisible manipulations to overcome a constraint on physical space. In this talk, we present a method for overcoming constraints on a higher-order narrative experience space. Narratives in interactive VR contexts must balance player choice with properties desired by the author, like story coherency or learning objectives.
For example, take a game like the Elder Scrolls V SKYRIM. In it, you can attack and remove enemies in the world. However, SKYRIM has an overarching narrative that depends on key characters performing key things at key times. And if you try to remove a key character from the world, you cannot. SKYRIM does not let you break the overarching narrative's coherency, leading to an inconsistent experience. We overcome this constraint by tracking player knowledge and shifting between alternate world mechanics. We call this method Invisible Dynamic Mechanics Adjustment. Now you may be wondering, why is this even needed? Well, it turns out that players notice inconsistencies even in low-fidelity environments, like for example, text-based choose-your-own adventures.
We first test whether players notice when visible world manipulations take place. People build internal representations called mental models when exploring an environment, reading a book, watching a film, or interacting in VR. Previous work in reading comprehension shows that contradicting a person's mental model while they read a short story creates a spike in reading time. We run a similar experiment in an interactive context, where a reading time spike when mechanics change indicates the manipulation is noticed by the player. We recruited 115 participants from Mechanical Turk to read 10 stories apiece. The stories are all set in the Wild West and create an expectation about the outcome of a choice the player will make. For example, in one story the player is a snake oil salesman who knows their elixirs have no healing properties. A consistent outcome is their elixir does not heal people. An inconsistent outcome is their snake oil cures a gunshot wound. We find that consistent outcomes are read on average 244 milliseconds faster than inconsistent outcomes. This is evidence that players do notice when visible manipulations occur.
So we cannot just change the world to accomplish what we want to do.
The author may have goals to achieve when controlling a narrative in VR, like making sure a character falls in love or that the player comes to understand a learning objective. The problem is, in a large interactive environment, the player can choose paths other than the one that leads to a narrative goal. This is similar to a non-symmetric game where the storyteller wins if a state is reached that achieves the goal and loses if the goal is never reached. By not committing to the full rules that govern the game world, the storyteller can jump between different game trees and reach more winning states than if it only used one set of rules. However, to maintain invisibility, the storyteller should not jump between game trees if it contradicts something the player knows. In order to make this assurance, we need a function that predicts what the player knows about the game world at any given time.
So how can we build this oracle that tells us what players know at any given time? In general, this is an open question, but we provide one solution: a microtheory. You can imagine a microtheory as made up of two things: a player log, or database of facts, and a set of observation rules to update that log. In essence, we track the player's knowledge by building it up as the player goes about. As the player plays, we check our rules, seeing which one might apply to update our log. We developed two microtheories. The conservative one says, the player will know about everything at their location. They see all the objects, all the properties of those objects, and all the actions that take place there. Ideal, I know, and likely very wrong, but at least we won't miss anything. The VR-specific one says, the player knows about things within their field of view, and in particular things within personal space, approximately 2 meters, and is aware of things within action space, approximately within 20 meters. Beyond that, we cannot say. Now, our current work is centered on testing how robust this model is, but there are several complications that we have to keep in mind. First, our work only used pre-existing real-world rules. We know that snake oil elixirs are not medicine. But then, what about rules that you learn only in-game? This happens with fictional items that have no real-world correlate, like potions themselves in The Legend of Zelda. What would you use to determine whether something's consistent or not? Would you maybe appeal to something about the game genre or even the game series to help decide what's consistent and what's not? Second, even though it's possible for players to notice when the world changes in an inconsistent way, change blindness is a relevant phenomenon. Can we create a microtheory that considers how stimuli may be just completely missed altogether, even when presented directly? In other words, can we be sensitive to the gorillas in our midst? Third, some inconsistencies are actually key to game experiences. For example, Antichamber intentionally breaks pre-established conventions and expectations about Euclidean space. This departure is the game's central conceit. You cannot help but think in Euclidean terms, and the game's non-Euclidean nature is the central challenge that you have to face. Fourth, some inconsistencies are so bad they end up being part of the convention of interaction for the game itself. These experiences, like for example, I Wanna Be the Guy, the movie, the game, walk a fine line between establishing and flaunting expectations throughout to deliberately create a challenging experience through frustration. Sometimes it works, sometimes it doesn't, but it crucially affects what we're trying to do here.
To recap, we've shown that dynamically manipulating VR simulation properties gives narratives more control while also retaining player choice. A model of player knowledge allows the manipulations to be performed invisibly by ensuring the world always appears consistent to the player. Finally, there is work to be done building robust knowledge models for players in VR contexts. We know that creating perceptually realistic worlds and tracking metrics like gaze is important, but modeling higher-level player cognition, like knowledge and intentions, is also important for full VR experiences. We invite others to cross the perception to event bridge with us and move beyond the event horizon. My name is Justice Robertson, and I am an incoming assistant professor at Kennesaw State University. I'm finishing a postdoc at the University of York.
And I am Rogelio Cardona-Rivera at the University of Utah. On behalf of the team, thank you for coming to our IEEE AI/VR 2020 talk. This work was sponsored in part by the Weaver Project at the University of York, a consortium of industry and academic teams building AI-driven predictive models and VR applications for data-driven storytelling in esports. For more information, visit www.weaver.tv.